One of the most important laws in chemistry is the law of conservation of mass. This law states that in any physical or chemical process, mass is neither created nor destroyed. Notice the specific exclusion of nuclear processes from this law. There are two ways that this law shows up in a balanced chemical equation. The first is the most obvious. In any chemical process, it must be the case that the sum of the mass of the products is the same as the sum of the masses of the reactants. This example shows the combustion of octane to produce carbon dioxide and water. Octane is the primary component of gasoline, so this is the primary chemical reaction that powers your car. The law of conservation of mass says that the sum of the mass of the octane plus the oxygen has to be equal to the sum of the mass of the carbon dioxide plus the mass of the water vapor produced by the chemical reaction. This idea can be used to figure out how much of a reactant is needed or how much of a product is produced, provided that you know the masses of all other reactants and products. For example, we can figure out how much hydrogen is needed to react with 56.6 grams of nitrogen to produce 68.12 grams of ammonia. The first thing I'm going to do is write some numbers in underneath my balanced chemical equation so that I can easily see which reactants and products I have information to go with. The next thing is to think about what the law of conservation of mass tells me. The law of conservation of mass tells me that the mass of the nitrogen plus the mass of the hydrogen must equal the mass of the ammonia, or NH3, produced. Now I can simply put the numbers into my conservation of mass equation and use a little bit of algebra to figure out that 12.06 grams of hydrogen must have been needed to react with the nitrogen to produce the 68.12 grams of ammonia. As we know, all macroscopic observations must have a microscopic explanation. With balanced chemical equations, the microscopic property that explains why mass is neither gained nor lost is that all atoms present at the beginning of the process are still present at the end of the process. This is our second interpretation of the law of conservation of mass. All atoms present as reactants must be present as products. Looking at the same example reaction, we can count the atoms to see that this has to be true. The red numbers in front of each chemical formula indicate the number of each molecule that participates in the reaction. This means that 2 octane molecules react with 25 oxygen molecules to produce 16 carbon dioxide molecules and 18 water molecules. The reason that the molecules react in this ratio is that this is the ratio that allows the process to finish with the same number and type of atom that were present in the beginning of the process. Looking on the reactant side of the equation, you can see that the process started with 16 carbon atoms, 8 atoms present in each of 2 octane molecules, 36 hydrogen atoms, 18 of them present in each of 2 octane molecules, and 25 oxygen molecules with 2 oxygens each gives us 50 oxygen molecules in the beginning. Looking at the product side of the equation, we can see that we still have 16 carbon atoms, 1 carbon atom in each of 16 carbon dioxide molecules, 36 hydrogen atoms, 18 water molecules with 2 hydrogens each, and my oxygen atoms still total 50, but are now split with 32 of them in the carbon dioxide and 18 of them in the water molecules. If all of the atoms present in the beginning of the process are still present at the end of the process, then it must follow that the total mass in the beginning is the same as the total mass at the end of the reaction.